Recording in progress.
Oh, sorry. Is that better? Okay. Morning, all.
Good morning. Audio check.
Yep, Raymond, good.
Hey, I thought I heard you. It's coming through a little soft. Maybe it's my side. Let me turn up my volume.
I'm on a new.
Oh, yeah. It's just my side. Sorry.
It is it? Okay. I was going to say I'm on a new computer, so who's got the read AI meeting notes? Okay. Let me just see if I can capture everybody here. Give a few people a few minutes as well. Brandon, it's your first time here, right? You're on mute if you're talking. Oh, you're not on mute anymore, but I can't hear you. Oh,
Can you hear me now?
I can now.
Ah, okay. Yes, you're correct. This is my first time on.
Okay, welcome aboard.
I appreciate it.
We'll do introductions later once we get going. And Michael, it's your first time, isn't it?
Yes.
Hi, Michael. Good to see
Hi.
you again.
Good to see you again.
Morning, Kevin.
Morning.
Gia. Oh, we've got a few more. This thing is making me admit everybody now. We've got to keep an eye on. Morning, Mitch. Morning, Vishal. Morning, Z.
Good morning, Alan.
Good morning, all.
Apologies for the delays, guys. I've got to keep admitting people to, I guess, there's the new rules of OCP Zoom. So I have to keep an eye on somebody in the waiting room, which is a bit annoying. Mitch. Vishal, is it your first time here?
Yeah, first time joining this one.
Okay. Okay, we're 8:05. We'll get going shortly. Just trying to collate all the names here. Is there anyone else trying to get into the room? No. Okay, so I got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's right. Okay, let me share my screen here. Hang on a minute. And the other thing is, yeah, we're recording by default, so that's good. Maybe 2 seconds. Okay, share screen. Allow. Share. Okay, can you see admit Hisham? Good morning, Hisham. Okay, so I think I've got everybody. I'll add you, Hisham, in it later. So, good morning, everyone. It's been about a month or so since we last met. A fair bit of water has gone under the bridge since then, and including the OCP Regional Summit that I attended. So that was a good show. I didn't give any presentations this year. Our submission wasn't accepted, unfortunately. But I did get a good update from a number of different people, which was very useful. So the main objective for today is, as I sort of said in the email, for everybody that saw the email, I've been working in the background with Vishal, who's on the call from Credo, and I've got some updates to the HPCM module concept that is a bit of a reboot based around the Credo Omni Connect, the very short reach channel connections, and which plays into what we've been saying in this work group for many years now. Is we want these modules, pluggable modules, to come very close together and try and reduce the I/O power to the locally attached devices. So what I really wanted to do is I've got some basic information here. I've done a sort of fair bit of work in the background, but I was just going to bring up the concept. I think most people, and actually, so we've got several new members here. So perhaps let's just get some introductions going. We like to do some introductions to the new attendees. Let's just start with Brandon. Would you like to kick off?
Can you hear me now?
Yes.
Sorry, my microphone is not playing well with Zoom today. Yeah, appreciate it. My name is Brandon Shekel. I work for Mainstream Engineering. We're sort of really new to this data center space. We're kind of exploring it now. Traditionally, our business is defense contracting, thermal management systems for defense systems. And yeah, we've created some interesting background technology that we think might have a fit in the data center world. And we're just kind of exploring that.
Okay. Welcome aboard.
Thank you.
And next, Michael Wee, would you like to introduce yourself?
Yes. Hi, everyone. I'm Michael from Creative, and our company just recently released our um, interesting technology of cooling with the DI water two-phase cooling solution. So we are seeking a chance to see this technology can be applied on a different field. I hope we can help. Thanks.
Yeah, welcome, Michael. So I met Michael at the OCP Regional Summit, and he gave a presentation at the Future Technologies Symposium, which was very interesting. On the again, as everybody who's been on this call regularly knows, I'm saying, can we make water work because it's so much better and cheap if you can get over its challenges. So anyway, and actually two-phase water was unbelievable. If you remember one of my regional summit presentations from a couple of years ago. So it was delightful to meet Michael, and maybe he can help us here. So that's him. And Vishal, would you like to give yourself a quick introduction?
Yep. Hello, everyone. My name is Vishal Shah. I am from Credo. Credo, as Alan mentioned earlier, I've been working with Alan on this technology called OmniConnect, which is currently first product is to use for memory disaggregation using our VS very short reach SerDes for the high performance computing. And yes, it has some great use cases and great capabilities in terms of how we can alleviate some of this bottleneck in this AI inferencing workload. So it's been quite exciting past few months as we talk to customers and talk about how what are the possibilities that can be brought together by this VSR memory disaggregation. So yeah, that's primarily what I work on at Credo, and look forward to hearing more about this group and exciting stuff going on. Thank you.
Great, thanks, Vishal. So I've not got as many slides as I'd like to go through, but I'm conscious we've got sort of a 50-50 split here of brand new people and old timers. So I was thinking that maybe a good place to start. I was just going to see if I can pull up some existing slides from the previous presentations I've done. Yeah, let's just quickly, if I bring up the video of that one.
We built a $49 garden hose
Hang
nozzle
on a
that
minute,
makes
sorry.
every pressure washer on the market completely unnecessary. Every pressure washer has the same fundamental flaw, and nobody was fixing it. You see, pressure washers.
Right. I got premium on my other accounts, but not on this one.
There we go.
So anyway,
Okay.
the reason what I thought I'd do here is if I first,
Here's a little
yeah.
animation. Basically,
So this is an animation of the HPCM module that we originally started with, or what we've been working on over the years in what was called the wall of compute. It was a composable modular system. So I'm just going to play this animation so you can see the constituent pieces. You're not going to get, we don't have time to really bring everybody up to speed, but this was a concept, and we did actually go for some funding, which unfortunately got didn't occur because of the change of government regime. But anyway, let me just play this little section a minute.
This module is roughly slightly bigger than an OAM, OCP accelerator module, but you'll notice that it also has the potential for media to be plugged in. So let me just play this animation. So there's 16 E3.S modules for media in memory to be attached to the module. It's a water-cooled jacket, and inside you see the module that's similar to the OEM. The key difference is this doesn't plug into a motherboard. It's got a bunch of backplane connectors for connecting modules together. If you people are familiar with servers of today with PCI Gen 5, you're probably seeing lots and lots more cables in these servers. It's because the PCBs are no good anymore. We need all these bypass cables. So, and on the back of on the other side of the card, we've got our big, powerful processor, accelerator, GPU, FPGA, AI device, whatever, that may be up to 1 kilowatt of power or more. And so, yeah, this module, this is a universal module where you can put any type of accelerator, heterogeneous accelerator on there, including switches, electrical switches, and even potentially optical switches in the near future. And you can even put your own custom accelerator into this footprint. So this gives us a heterogeneous high-performance building block. Just putting that back together, it reassembles a water jacket. You'll see as it moves the power pins and the water inlet. And this module then plugs into a wall. So this is one small section of the wall carrying the water and the power, 48 volts, and the module mates into the wall, blind mates into the wall. And then, so now this will move on as well. You will see this module. This is one individual module in one slot of the wall. But here's an example of a small wall with 8 modules tall and 16 modules wide. And you can plug in your modules into that wall and heterogeneously as well, any mix and match. The idea is this is a fully open standard that everybody would comply to. And this would allow you to build any node configurations that have already existed today in any software stacks. So as a couple of examples, the Frontier supercomputer is a EPYC CPU and 4 MI250X GPUs, and there's two of those nodes inside a 1U chassis. We could replicate that with these 10 modules here, and we would replicate the interconnect of that platform by putting the cables to wire these modules together explicitly as Frontiers has done. Or you can convert it to your own domain-specific needs if you have different needs for different bandwidths and feeds between CPUs and GPUs. Another example is we could emulate the Grace Hopper configuration. If you know the Grace Hopper from NVIDIA, they have something like 7 times the PCI bandwidth or 1 PCI Gen 5 channel between the Grace and the Hopper chip.
All right, I'll stop it there. Basically, this carries on to show you a lot of different configurations of existing systems or mixing your own. We then were talking about an FPGA emulation platform, building that, and that was where our collaboration, our request for funding came from, with about 7 companies, some of whom are on this call. We were all contributing towards. And in this presentation as well, I want to just see if this presentation, it goes into the details. Yeah, this is specifically, it's an older original presentation. But anyway, so hopefully that gives you a flavor of what it is we've been up to over the years. So what I'm going to show you now is, and by the way, that wall of compute it was our extreme version. We've done we moved on to sort of some bring up versions in the OCP DCMHS platform, if you're familiar with that. Because obviously the wall was seen as a maybe a radical step too far, but possibly good for some of the edge applications. Anyway, so it's the module I wanted you to sort of really get your attention. So so there's a couple of things that have been happening since. Oh, hang on a minute. Let's admit that person. There's a few things that have obviously been happening over the last few years with the AI, and AI inference has obviously become hotter and hotter. And obviously, we've got all these HBM implementations. But one of the things that's sort of stuck out really, because one of the directions, again, for those of you that go far enough back with me with these concepts, we were looking at AI like 4 or 5 years ago at the ramp of the need. And I think it was the likes of Alibaba and a few other in fact, the Chinese companies were showing models getting up to 10 terabytes in size, really large need for memory. But if you're following the AI inference game now, we're finding that the context size, not only are the models getting massive, but also the context size where you're in the KV cache that you need to swap in as your context grows in a conversation or an agentic AI operation. And so that causes you to spill out of HBM, and then you have to roll up the memory hierarchy either out to the CPUs that have maybe a terabyte or so of memory, or stroke and roll out to storage. And obviously you get the decrease in bandwidth as that, and then there's a cost. So if you've been following Jensen in his keynotes at GTC, they're talking now about that becoming a problem, and they've got this CMX, this scale out to the to masses of storage to be in very optimally configured to try and pull this in, because it's becoming a bit of a problem in terms of stalling everything with having to bring the data in to the HBMs more and more frequently at much slower rates. So I mean, that was a use case that we've been sort of looking at in terms of the work I've been doing with Credo. And so again, so on the Credo context, I don't have any specific information here going into the details of what they're offering. I'm just going to show you some images here. We can maybe jump to some presentations that I've given in this meeting a few weeks back. And so we can dive wherever we want here. I just wanted to get a quick context in the form of the module sense and say that this could be a real project that I'd like to really pull the thread on, which we certainly do have commercial interest for. So whereas I guess that was one of the things we were always searching for, and we had this emulation platform shown here is our starting point before, but with this we potentially have the need for ever-growing context, and KV cache size could be a good specific application for what I'm about to show. Any quick questions there before I dive into the new stuff? I know it might be a lot for the newbies, but okay. All right, let me just jump into this presentation then. Okay, so now you've got the little backdrop of that module that I explained from that previous presentation. And by the way, again, for the new people, if you go to the OCP HPC wiki, that recording I just showed you was in the welcome section. There's a number of videos from the presentations I've given over the time, and just a minute. I've lost control of my mouse. Admit. All right, hopefully you're back in, Z. And so you can watch those videos or look at the slides, and you can get a quick study on what we've done over the years, and it'll give you a bit more context, which might be useful. Okay, so this reboot is really around an AI inference with large context target application. But I think it applies very applicably to a lot of the HPC stuff still. But obviously, AI is a big kahuna in the room. So I just want to jump straight in. This is the module as it stands as a concept right now. So what I'll do is I'll quickly go through. I'm not sure if I can do an annotate. Can I do a pointer? I don't seem to have. Sorry, guys. Just trying to, for some reason, when I'm in this presentation mode, I don't see a mouse. Let me just get rid of that. Let me just make the slide big. Okay. Can you all still see that? Okay.
Yep, it's fine.
Okay. Now I can't progress the slide. Right, there we go. All right, now you can see my mouse. That's good. Okay, so this module right now, so this is a very early concept, right? At the moment is 120 millimeters by 120 millimeters in size. So it's actually quite a bit smaller than the modules we've been doing to date. Again, this is very tightly packed right now, so it may or may not be viable. So I've got more work to do on this, but this was a quick first pass. So a couple of things that you can see here. So this is actually, we've talked about actually taking the module to a substrate. Why bother with a package? And I think it becomes critically important here because you are dealing with a lot of transceivers, which makes these packages huge if you go to a traditional package. So what you're seeing in the middle here is a full reticule size die. And the idea here as well is as we look at standardization, if you've been following the open chiplet economy, with the chip, we're trying to standardize chiplets for everyone else. Obviously, chiplets have been very well established in the big guys, and obviously doing that very vertically themselves. But we want chiplets for the rest of us, right? So the idea here is and the problem with putting multiple die down is you've got yield issues to deal with, testability issues to deal with. If things go wrong and you get an expensive mistake, who has to pay and all the rest of it. So establishing an ecosystem is a slow process right now. But with this approach, what we've got here is we've got this full reticule size die. We're on a substrate, so this is substrate material, so we get the substrate routing capabilities. And the I/O of the OmniConnect actually is a very short reach, an IEEE standard, very short reach I/O at the moment. And so it can still reach of the order of 200 millimeters or so. So it can still do a decent distance even outside of a package, but it allows a lot more denser I/O beachfront bandwidth per millimeter, and a lot less area for the actual I/O IP. So you have more area for your compute. So that's the bottom line there. So what we've done is in these connectors, north and south, are the co-packaged ones. So the ones I've got here, by way of example, are the Samtec stroke Molex ones. I think they've got a collaboration on the CPX. So the co-packaged copper connectors are the ones we've got here. And that's 128 transceivers, 64 north, 64 south. And then on the sides here, you're seeing 50, 25 modules per column, 50 pluggable modules. So just like that previous video I showed you, where it used to be the EDSFF, which are really quite large modules, these are actually very small memory modules. Each one of these is a 256 gigabyte memory, as I will show you shortly. And so this gives you potentially, and this is, this is all based on, you can get about 50, each Weaver buffer, each memory module has 12 transceivers right now. And so this basically you need 600 transceivers, and you can fit 300 transceivers per edge of a full reticle size die. So this is a conceptual, based on what you should be able to achieve with the full reticle size die. What else was I going to say? So this gives you 10 terabytes of memory, and the bandwidth added up of all of these. Each memory module, as I'll show you later, is basically LPDDR5X based. So it's a lot lower cost than HBM as well. And each of these modules are individually pluggable. So you've got a very good serviceability capability here as well. So that's basically, is there anything else I want to say on this particular slide? Any questions on this slide? I'm going to show you a little bit more of the memory module in a moment. Okay. A minute, gotta go back to here. Forward to the next slide. Yeah, this is an exploded view. So this exploded view can just, so you get a little bit better gist. So you can see that each of the modules is individual. They all have their own connectors. And these are derived from the M.2 connector. If you're familiar with the little M.2 SSDs you have in your laptop, the sticks, it's based on that. It's got more pins. It's 108 pins is what we need for this implementation. So we would need to customize this connector if that's possible, and that was what I would like to get from our colleagues on the call. In fact, I see Zizon from Amphenol. This is this model is from an Amphenol connector that I've sort of stretched a little to sort of just, so I've used it as a base starting specification. The M.2 connector, which I'll get into a bit more detail in a moment. Here you can see the exploded view of the CPX. This is the CPX receiver, and this is a CPX cables there when it's plugged in. And I think that's everything on there, just so you can see the constituent pieces. And then really finally, the module itself. So you can see on the module, this module is actually 4 millimeters thick. So it consists of a front and a back heatsink, and then, as you can see here on this module, we've got 2 LPDDR5 memories on the front and the Weaver buffer die, and we have 2 LPDDR5Xs on the back. So a total of 4 memories. You can get about 64 gigabytes. I think there might even be talk about 128, but let's just stick with 64 for now. 64 gigabytes per chip. So you've got a 256 gigabyte module here. Now, interestingly, I think just on LPDDR in general, one of the issues that has been a concern of using LP memory, certainly in enterprise class versus DDR5, has been that its RAS capabilities are not necessarily anywhere near as good as what they've done with DDR over the years. Now that's been changing, and there's a lot of ECC built in, a lot of channel error correction in error monitoring built in, and interestingly, at the regional summit, Meta specifically gave a presentation in their keynote. Were definitely worth watching, and they were saying, "Hey guys, we need to start to think about using LPDDR6, or they talked about 5, and they did a nice little chart of its capabilities versus DDR5." And its merits, and it wins on everything, except for maybe the RAS. And they were claiming that LPDDR6 will close the RAS gap completely. And so I was predicting that DDR5 should have been stillborn years ago. But obviously the CPU vendors kept it going. But I'm pretty sure that DDR6 doesn't make sense if LPDDR6 really does cover the RAS and the enterprise needs. And when you can get 256 gigabytes in a module this small, by the way, this module is 40 millimeters long and 23 millimeters tall, with 256 gigabytes and a lot lower power than a DDR5. And again, those of you that follow me know that I was pushing the OMI DDIMM at the time, the IBM OMI serial attached DRAM memory. And so this is very similar to that. So you'll recognize some similarities to what I've been doing there. But obviously that OMI memory has DDR5. So those modules are sort of large EDSFF size modules, E3.S type size. So the other key thing about this module is it's got 12 transceivers on it for the 4, and those transceivers are going at 112 gigabits per second. So it's basically 3 transceivers per LP memory is what you've got there. Okay, so that's that. And then so on the signal integrity side, you can see here it's an Amphenol connector that I just stretched, and so the pins are not right, but I just stretched it to support 108 pins, so 54 on both sides. So the only other thing about this is the cooling. Now I was trying to get that into a slide, but I didn't get a chance. So let me just show the cold plate off. So I was separately doing some thermal analysis on this, some very crude thermal analysis with the help of AI, I will confess. So I played about with a lot of concepts of how to cool this. Each module is of the order of 17-ish watts for all the memory in the buffer. And I was looking at various ways of liquid cooling this. I wanted to keep the pluggability of the module. And long story short, it made sense. In fact, you know what? Let me just let me just see if I can. I'm not sure if I'm going to be able to do this. Let's try that. Okay, so here you can see in the heatsink, not readily viewable here. Hang on. The lighting of this is not brilliant. There you go. So here you can see that this basically lays on top of the die, and essentially it creates a thermal path mainly up to this thicker lid piece. And I've done that on both sides. And the memory obviously is a big area already, again, conducting up to the top. So we're extracting the heat out of the top. And that's the idea, is I'm conducting the heat out of the top. So a full thermal analysis does need to be done on this. It was a crude 2D analysis I've done. The back heatsink is just the memories, obviously. And so that's how we bring the heat. So the heat is being brought all the way up to all of these modules, to the top of these modules. And then effectively I'm putting a heat sink cap on top. And again, this is just this little separate thing that I've done in terms of the thermal analysis of this, is just a one row of 25 modules. And then I've got this little cold plate top hat that I popped onto it just by itself. And you can see I've got an inlet, I've got an outlet. And the best thing to show here is if I bring that there, if I go into a section view, there we are. Why is that like playing ball? All right. Let me just, here's the one I did earlier. What is just going on there? There we go. All right, so here's a section view that I did earlier. So you can see the inlet water is coming in. It comes into the chamber here, and then the water flows across the top, a thin channel across the top of each of the modules, and then returns out the other side. So that's how I was capturing the heat. I do have some additional slides where I did actually do the thermal analysis. It on the face of it, it all looks okay. But so just going back to the slide deck again, if we go back to this one. So where my head's been on this, and again, this is very early days, is it the actual, we would actually build a heat sink that would wrap across the top of these. So the liquid would come in, it would enter across the tops of these modules first. So coming from both sides into the middle, it would then drop down onto the XPU die, and then it would come out from the XPU die into a sort of a chamber above, a little expansion chamber, and this is related to what Michael's doing, Michael Wee on the call with some of his concepts, and where we could potentially have some 2D, some two-phase boiling going on here as it comes out the top of this die. And again, for those of you that have followed me on the wall of compute, I've also got a preference for this, for the die being on the other side of the module, so that you actually have a liquid base on the back side, and it's dry on the top. And so a bit like you saw the way the module was sandwiched together in the video at the beginning. So I'm looking into ways of doing that. I think I have a preference for this die going on the back. Now, the astute of you might say, where's all the power? We would go to vertical power with this. So in this scenario, the power is going to be all on the bottom of the module. And obviously, if we push this die to the back, then the power will be in this area on the top. So that pretty much sums it up. I guess the main advantages here, if we can do this, is that the actual substrate is literally the one expensive XPU in a ton of connectors, right? And so I've called this for a long time like pluggable chiplets. So again, in the chiplet world, as we get this going, this bootability, sorry, the getting it up and running is a challenge, and the yield, the testability, serviceability is all a big deal of creating an ecosystem. Whereas this approach would really allow us to get to that level where this module ends up being not actually of the same order of magnitude as a SXM module, but instead of having 288 gigabytes of HBM4 like Ruben does, we have 10 terabytes of LPDDR. And so you're getting a better balance. You're getting high bandwidth memory. This will do eight terabytes per second for the module. So you're not getting 22 terabytes per second that you get with HBM on a Ruben, but you're getting 8 terabytes, a very respectable bandwidth, all the way up to 10 terabytes. Whereas if you take a Vera Rubin architecture, as soon as you need to spill into the Vera next door to the Rubin, you're limited to around about maybe a 1.8 terabytes or maybe less, 900 gigabytes to the it's 1.2 actually. The LPDDR bandwidth is 1.2 terabytes per second on a Vera, and it's 1.5 terabytes of capacity. So every Vera will give you 1.5 terabytes, and then you'd need to spill via either the network or PCI to CXL. And if you spilled that way, then you're down to PCI bandwidths, which are of the order of 64 gigabytes per second for a single PCI channel, which Vera, I believe, only has 32 lanes of PCIe at my last guess. So this keeps the bandwidth massive for much higher capacities. That's the value prop anyway. Plus, obviously, from a chiplet, by the way, these modules don't necessarily have to be memory. They could also introduce they could be an I/O buffer or I/O translator as well. And one final point as well, where we see these CPX connectors, you may have heard Credo have been sort of marketing, certainly on LinkedIn, quite a bit about their new OmniConnect micro LED I/O. So we could be introducing micro LED I/Os into this module format as well, like I've presented on the Avicenna in the past with our module concepts. The micro LED, which I think is a fascinating low latency, low energy optical I/O alternative to silicon photonics, certainly for local connections. So I've said an awful lot there. We got 10 minutes left. Any questions or comments?
Alan,
Actually, so just the two takeaways here is I want the connector guys to say, am I crazy for saying this M2 vertical connector we can get to 112 gig? And the liquid cooling is the other one is can we liquid cool this? And Michael, if we could see if we can find a way to cool this with two-phase water, that would be really exciting. Okay.
Yeah, Alan. So my first question actually is related to what you just said about the connector that you want for the memory module.
Yeah.
So I think you mentioned the memory is going to be based on LP5X, right? So that's
Yeah.
So you need the connector to be single-ended signaling, right?
No. So the buffer, the Credo Weaver buffer translates that to 12. The four memories get translated to 12 transceivers, 112 gig each.
Those are differential.
Yeah, it's differential.
Okay.
So it's
The
112
form factor
gig.
is similar to a M.2 M.2
Yes.
form factor?
Yeah. So basically, the reason it's M.2 is it's, well, one, I need it to be really thin anyway, if we're going to be able to achieve this density. But it's substrate material. Again, we're putting a die down here, and we need the substrate level routing capability. So it's going to be a 0.8 millimeter PCB, which the M.2 is designed natively to support, and at point 0.8 rather than the 1.54 of the EDSFF. And it's a 0.5 millimeter pitch as well on the IO. So basically, it faithfully follows M.2 at that level, but it's got more pins, and the keying would be simpler. There is no middle key or anything. But what we need is, obviously, at the moment, I think M.2's only go up to PCI Gen 4 speeds. And so, but it is a vertical connector. A lot of M.2s are horizontal, so they've got very complex connectors. The vertical one is very simple. So I'm hoping that the signal integrity, on the basis you made it there with the 112 gig with EDSFF, in my head, it should be equally achievable with the M.2, but you're the experts, not me. Does that
Do
all
you
make sense?
have any maybe slightly more detailed drawing of the connector, the card edge, that will help me visualize?
Yeah, sure. I mean, basically, it's a standard M.2. So the model is auto
Okay.
scale. I can send you a step file of the model. The connector I've just used a standard M.2 and I've stretched it. So ignore all the pins. You'll see the gold fingers. The gold fingers are correct on the board, but the connector is just an Amphenol connector that I've just stretched, an M.2 one that I've just stretched.
Okay, so your gold finger right now is um coming straight over M.2. Okay.
Yeah, that's the idea. It'd be Goldfinger and TN.2, yeah.
And by the way, for the 4 CPX, uh you are envisioning something like PCIe type of I mean
So
length.
that CPX is already rated at 200 gig. So people could put anything on there, or they could use the OmniConnect VSR again, which is 112 gig. But those connectors, I believe, are rated for 200 gig. They're sort of targeting a Broadcom switch, a 100T 100T to a Broadcom switch.
Okay, so potentially could be Ethernet based I/O linking memory module to something else.
Yes, it could be an
Okay.
Ethernet I/O straight out the XPU, whatever the XPU designer wants. But that's just showing that there are 128 transceivers coming out, yeah, for the I/O piece, and with 50 memory modules for the memory piece. Yeah, makes sense.
Yep. Thank you.
Alan, for the cooling part, um, is it you mentioned about liquid cooling? Is it possible to do air cooling on these modules?
Um, the way this is currently set up, that the concept I put together was for liquid cooling.
Hmm.
But that's a good question, Vishal. Let me just flip back because there is some subtleties there that I didn't mention that I should have. So again, if you've got one heatsink, one liquid cooled heatsink that you mount on this, you're going to want the thermal grease, the best TIM interface on the die, right? And you've got two interfaces that you need. So I modeled these modules. The heatsink, you'd have thermal putty on the top of these, which is a bit more compliant. And I found some, decently rated stuff that would actually work with this in my crude simulations. So everything's crude here and needs proven with proper simulations with thermal experts. but yeah, so you would get the putty mate to these and the tight thermal interface to this. Now, in theory, if you look at Blackwell, for instance, from NVIDIA, they liquid cool obviously that one in most situations, but they're backwards compatible to their DGX, HGX boxes, and where they actually put a massive tall heatsink, and I think they're in a 6U box now. I think the heatsink is of the order of 5U high, where you have heat pipes coming from the GPU. And so, technically speaking, we could put a big tall heatsink on top of this, and with heat pipes from the tops of the memories and the XPU.
Sorry,
And
Alan, you're not sharing, but just in case if you are trying to show
oh,
something.
really? Sorry, I thought it was. So how long have I not been sharing? Hang on a minute. Let me go back to the. It was just the other slide. It was just there we go. So this one. So I was just saying that the tops of these memories, we would put putty on. So when you make the heat sink, there's a bit more compliance, and your very tight thermal interface will be on the XPU itself. The actual density of the heat flux on the memories is a lot less than the density, obviously, on the die. So anyway, so a very tall heatsink. Uh, if you're familiar with the old DGX boxes or the OCP OAI chassis, they used to have 4U. It'd be in a 4U box with like a 3U type heatsink, but now they've gone to like a 5U heatsink to cool a 1.2 kilowatt Blackwell chip. So the total energy here, these memories add up to about 300 watts total. And assuming the GPU is of the order of it's just a reticule sized die. So if you say that's of the order of 700 or 800 watts, then we're in the sort of kilowatt territory of this complete module. But it's a bit more thermally distributed, so I don't see any reason why it couldn't be air cooled in a tall stack, a tall heatsink with the vapor chamber pipes going up the heatsink. Does that make sense, Vishal?
Sorry, I was muted. Yeah, makes sense. Yeah, thanks.
Okay. I see we had a few people join while we were chatting. So hi Howard, hi Bobby. I see Howard and Bobby joined, and two Bobbies actually.
Hey, Alan. I know the close to the time, so I just have a quick question. I didn't see the supporting feature for those modules.
Yes, good question. So on the support, uh, yes, I think we can do some basic supporting around it, but equally, so I was thinking there would be a structural frame. This is where the module might grow. So this is like my first pass. So I shouldn't have stopped sharing, should I? So I was thinking that you will have some base frame around here that will capture these, but obviously um, uh, that's so latching these in place is one thing. I was wondering if potentially we could maybe stick like a bar down all of these that we could sort of latch them in. But absolutely, that's a good question. In terms of being retained, when you put the heat sink on, they're going to be retained very nicely. But when you come to take it off, you will unplug all the modules as you take it off because the putty will stick to the heat sink. So I think I was trying to think of some novel ways of doing this, but I haven't solved that one yet. So yeah, how do we retain these is a good question.
Hey, Alan, one final question.
Yep.
So the central die is mounting on substrate. So on the current slide, all the green thing, those are closer to package material than PCB material,
Yeah,
correct?
this has to be substrate material. Yeah.
Right. Okay.
The density of the interconnect and you got to break out of the die. So we need to be in substrate, organic substrate.
Okay. And I think you say right now your concept is 120 millimeter by 120 millimeter.
Yeah, I sort of said
Okay.
in the email, I said less than 150 by less than 150. I think we might have to grow to about maybe 130 or 140, just from this initial. I mean, I've packed it in here, obviously. Okay, so I think they're marching. I mean, for me, so this is real. Vishal and I are looking into how to maybe sort of build it. And by the way, we don't have to do this with bare die to begin with. We potentially have some partners that could bring die to the table. We also can do this with a packaged FPGA, for example. So we could redo that FPGA module. Obviously, the module will be much bigger and there'll be less transceivers. So I am looking at some prototype versions that we could do with FPGAs. And obviously you wouldn't have 50 memories because you don't have enough transceivers coming off the FPGA. But we can do something that could be in keeping with this concept because the nice thing about these VSR transceivers is they can talk to LR transceivers like on a standard FPGA. So we could use this for FPGA emulation platform again. I realize we're over time, guys. So I just want to make sure I captured everybody. There's a few people that joined. So hi, Bobby Lou. Hi, Bobby Joseph. Michelle, Joe, Raymond. I think I've got everybody. All right. Well, thank you, guys. We'll continue in the next meeting. And then if any of the connector guys and thermal guys want to touch base with me sooner on this on the connector design, that'll be great. Okay.
Thanks, Alan.
Thank you.
Thanks, guys.
Thank you, Anne. Bye.